Hey guys, and welcome to a brand new tutorial series on neural networks with Python and Tensorflow 2.0. Now, Tensorflow 2.0 is the brand new version of Tensorflow, still actually in the alpha stages right now, but it should be released within the next few weeks. But because it's an alpha, Tensorflow has been kind enough to release us that alpha version, so that's what we're going to be working with in this tutorial series. And this will work for all future versions of Tensorflow 2.0, so don't be worried about that. Now, before I get too far into this first video, I just want to quickly give you an overview of exactly what I'm going to be doing throughout this series so you guys have an idea of what to expect and what you're going to learn. Now, the beginning videos, and especially this one, are going to be dedicated to understanding how a neural network works. And I think this is absolutely fundamental, and that you have to have some kind of basis on the math behind a neural network before you're really able to actually properly implement one. Now, TensorFlow does a really nice job of making it super easy to implement neural networks and to use them, but to actually have a successful and complex neural network, you have to understand how they work on the lower level. So that's what we're going to be doing for the first few videos. After that, what we'll do is we'll start designing our own neural networks that can solve the very basic MNIST data sets that TensorFlow provides to us. Now, these are pretty straightforward and pretty simple, but they give us a really good building block on understanding how the architecture of a neural network works, what are some of the different activation functions, how you can connect layers, and all of that, which will transition us nicely into creating our own neural networks using our own data for something like playing a game. Now, personally, I'm really interested with neural networks playing games, and I'm sure a lot of you are as well, and that's what I'm going to be aiming to do near the end of the series on kind of our larger project. We'll be designing a neural network and tweaking it so that it can play a very basic game that I've personally designed in Python with Pygame. Now, with that being said, that's kind of it for what we're going to be doing in this series. I may continue this on in later videos and do like very specific neural network series, maybe a chatbot or something like that. But I need you guys to let me know what you'd like to see in the comments down below. With that being said, if you're excited about the series, make sure you drop a like on this video and subscribe to the channel to be notified when I post the new videos. And with that being said, let's get into this first video on how a neural network works and what a neural network is. So let's start talking about what a neural network is and how they work. Now, when you hear neural network, you usually think of neurons. Now, neurons are what compose our brain, and I believe, don't quote me on this, we have billions of them in our body or in our brain. Now, the way that neurons work on a very simple and high level is you have a bunch of them that are connected in some kind of way. So let's say these are 4 neurons, and they're connected in some kind of pattern. Now, in this case, our pattern is completely like random. We're just arbitrary. We're just picking a connection, but this is the way that they're connected, okay? Now, neurons can either fire or not fire. So they can either be on or off, just like a 1 or a 0, okay? So let's say that for some reason, this neuron decides to fire. Maybe you touch something, maybe you smelt something, something fires in your brain, and this neuron decides to fire. Now, it's connected to, in this case, all of the other neurons. So what it will do is it will look at its other neurons and the connection, and it will possibly cause its connected neurons to fire or to not fire. So in this case, let's say maybe this one firing causes this connected neuron to fire, this one to fire, and maybe this one was already firing and now it's decided it turned it off or something like that, okay? So that's what happened. Now, when this neuron fires, well, it's connected to this neuron, and it's connected to this neuron. Well, it's already got that connection, but let's say that maybe when this one fires, it causes this one to unfire because it was just fired. Something like that, right? And then this one, now that it's off, it causes this one to fire back up, and then it goes, and it's just a chain of firing and unfiring, and that's just kind of how it works, right? Firing and unfiring. Now, that's as far as I'm going to go into explaining neurons, but this kind of gives us a little bit of a basis for a neural network. Now, a neural network essentially is a connected layer of neurons, or connected layers, so multiple of neurons. So in this case, let's say that we have a first layer. We're going to call this our input layer that has 4 neurons. And we have one more layer that only contains 1 neuron. Now, these neurons are connected. Now, in our neural network, we can have our connections happening in different ways. We can have each, neuron connected to each other neuron, so from layer to layer, or we can have like some connected to others, some not connected, some connected multiple times. It really depends on the type of neural network we're doing. Now, in most cases, what we do is we have what's called a fully connected neural network, which means that each neuron in one layer is connected to each neuron in the next layer exactly one time. So if I were to add another neuron here, then what would happen is each of these neurons would also connect to this neuron one time. So we would have a total of 8 connections because 4 times 2 is 8, right? And that's how that would work. Now, for simplicity's sake, we're just going to use one neuron in the next layer just to make things a little bit easier to understand. Now, all of these connections have what is known as a weight. Now, this is in a neural network specifically, okay? So we're going to say this is known as weight 1, this is known as weight 2, this is weight 3, and this is weight 4. And again, just to reemphasize, this is known as our input layer because it is the first layer in our connected layers of neurons, okay? And going with that, the last layer in our connected layer of neurons is known as our output layer. Now, these are the only 2 layers that we really concern ourselves with when we look and use a neural network. Now, obviously, when we create them, we have to determine what layers we're going to have and the connection type. But when we're actually using the neural network to make predictions or to train it, we are only concerning ourselves with the input layer and the output layer. Now, what does this do and how do these neural networks work? Well, essentially, given some kind of input, we want to do something with it and get some kind of output, right? In most instances, that's what you want. Input results in an output. In this case, we have 4 inputs and we have 1 output. But we could have a case where we have 4 inputs and we have 25 outputs, right? It really depends on the kind of problem we're trying to solve. So this is a very simple example, but what I'm going to do is show you how we would, or how a neural network would work to train a very basic snake game. So let's look at a very basic snake game. So let's say this is our snake, okay? And this is his head. Actually, yeah, let's say this is his head, but like this is what the position of the snake looks like, where this is the tail. Okay, we'll circle the tail. Now, what I want to do is I want to train a neural network that will allow this snake to stay alive. So essentially, its output will be what direction to go in, or like to follow a certain direction or not. Okay, essentially just keep this snake alive. That's what I want it to do. Now, how am I going to do this? Well, the first step is to decide what our input is going to be, and then to decide what our output is going to be. So in this case, I think a clever input is going to be, do we have something in front of the snake? Do we have something to the left of the snake? And do we have something to the right of the snake? Because in this case, all that's here is just the snake, and he just needs to be able to survive. So what we'll do is we'll say, okay, is there something to the left? Yes, no. Something in front? Yes, no. So 0, 1. Something to the right? Yes, no. And then our last input will be a recommended direction for the snake to go in. So the recommended direction could be anything. So in this case, maybe we'll say the recommended direction is left. And what our output will be is whether or not to follow that recommended direction or not, or to try to do a different recommendation, essentially, or go to a different direction. So let's do one case on how we would expect this neural network to perform without once it's trained, right, based on some given input. So let's say there's not something to the left. So we're going to put a 0 here because this one will represent if there's anything to the left. The next one will be front. So we'll say, well, there's nothing in front. The next one will be to the right. So we'll say right. And we'll say, yes, there is something to the right of the snake. And our recommended direction can be anything we'd like. So in this case, we say the recommended direction is left. And the way we'll do the recommended direction is -1, 0, 1, where -1 is left, 0 is in front, and 1 is to the right, okay? So we'll say in this case, our recommended direction is -1, and we'll just denote this by direction. Now our output, in this instance, should either be a 0 or a 1, representing do we follow the recommended direction or do we not? So let's see, in this case, following the recommended direction would keep our snake alive. So we'll say 1, yes, we will follow the recommended direction. That is acceptable. That is fine. We're going to stay alive when we do that. Now, let's see what happens when we change the recommended direction to be right. So let's say that we say 1 as our recommended direction. Again, this is Dern here. Then what should our output be? Well, if we decide to go right, we're going to crash into our tail, which means that we should not follow that direction, so our output should be 0. So I hope you're understanding how we would expect this neural network to perform. All right, so now how do we actually design this neural network? How do we get this to work? How do we train this, right? Well, that is a very good question, and that is what I'm going to talk about now. So let me actually just erase some of this stuff so we have a little bit more room to work with some math stuff right here. But right now, what we start by doing is we start by designing what's known as the architecture of our neural network. So we've already done this. We have the input and we have the output. Now, each of our inputs is connected to our outputs, and each of these connections has what's known as a weight. Now, another thing that we have is each of our input neurons has a value, right? We had, in this case, we either had 0 or we had 1. Now, these values can be different, right? These values can either be decimal values or they can be like between 0 and 100. They don't have to be just between 0 and 1, but the point is that we have some kind of value, right? So what we're going to do in this output layer to determine what way we should go is essentially we are going to take the weighted sum of the values multiplied by the weights. I'm going to talk about how this works more in depth in a second, but just follow me now. So what this symbol means is take the sum, and what we do is I'm going to say in this case I, which is going to be our variable, and I'll talk about how this kind of thing works in a second. We'll say I equals 1, and I'm going to say we'll take the weighted sum of, in this case, value I multiplied by weight I. So what this means essentially is we're going to start at I equals 1. We're going to use I as our variable for looping. And we're going to say, in this case, we're going to do V1 times VI times WI. And then we're going to add all of those. So what this will return to us actually will be V1 W1 plus V2 W2 plus V3 W3 plus V4 W4. And this will be our output. That's what our output layer is going to have as a value. Now, this doesn't really make much sense right now, right? Like, why are we doing this weights? What is this multiplication? Well, just follow with me for 1 second. So this is what our output layer is going to do. Now, there's one thing that we have to add to this as well, and this is what is known as our biases, okay? So what we're going to do is we're going to take this weighted sum, but we're also going to have some kind of bias on each of these weights, okay? And what this bias is known as, it's denoted by C typically, but essentially it is some value that we just automatically add or subtract. It's a constant value for each of these weights. So we're going to say all of these connections have a weight, but they also have a bias. So we're going to have B1, B2, B3, and B4. Well, we'll call it B instead of C. So what I'll do here is what I'm also going to do is I'm also going to add these biases in when I do these weights. So we're going to say BI as well. So now what we'll have is we'll have at the end here plus BI or plus B1 plus B2 plus B3 plus B4. Now again, I know you guys are like, what the heck am I doing? This makes no sense. It's about to make sense in 1 second. So now what we need to do is we need to train the network. So we've understood now this is essentially what this output layer is doing. We're taking all of these weights and these values, we're multiplying them together and we're adding them and we're taking what's known as the weighted sum, okay? But how do we, like, what are these values? How do we get these values? And how is this going to give us a valid output? Well, what we're going to do is we're going to train the network on a ton of different information. So let's say we play 1,000 games of Snake and we get all of the different inputs and all the different outputs. So what we'll do is we'll randomly decide like a recommended direction and we'll just take the state of the snake, which will be either is there something to the left, to the right, or in front of it, and then we'll take the output, which will be like, did the snake survive or did the snake not survive? So what we'll do is we'll train the network using that information. So we'll generate all of this different information and then train the network. And what the network will do is it will look at all of this information and it will start adjusting these biases and these weights to properly get a correct output. Because what we'll do is we'll give it all this input, right? So let's say we give it the input again of 0, 1, 0, and maybe 1, like this is just a random input. And let's say the output for this case is, what do you call it? So 1 is go to the right, the output is 1, which is correct. Well, what the network will do is say, okay, I got that correct. So what I'm going to do is I'm not going to bother adjusting the network because this is fine. So I don't have to change any of these biases. I don't have to change any of these weights. Everything is working fine. But let's say that we get the answer wrong. So maybe the output was 0, but the answer should have been 1, because we know the answer, obviously, because we've generated all the input and the output. So now what the network will do is it will start adjusting these weights and adjusting these biases. It'll say, all right, so I got this one wrong, and I've gotten like 5 or 6 wrong before, and this is what was familiar when I got something wrong, so let's add 1 to this bias, or let's multiply this weight by 2. And what it will do is it'll start adjusting these weights and these biases so that it gets more things correct. So obviously that's why neural networks typically take a massive amount of information to train, because what you do is you pass it all of this information and then it keeps going through the network, and at the beginning it sucks, right? Because it has this network just starts with random weights and random biases. But as it goes through and it learns, it says, okay, well, I got this one correct. So let's leave the weights and the biases the same, but let's remember that this is what the weight and the bias was when this was correct. And then maybe it gets something wrong and it says, okay, so let's adjust bias 1 a little bit. Let's adjust weight 1. Let's mess with these, and then let's try another example. And then it says, okay, I got this example right. Maybe we're moving in the right direction. Maybe we'll adjust another weight. Maybe we'll adjust another bias. And eventually your goal is that you get to a point where your network is very accurate because you've given it a ton of data and it's adjusted the weights and the biases correctly, so that this kind of formula here of this weighted average will just always give you the correct answer, or has a very high accuracy or high chance of giving you the correct answer. So I hope that kind of makes sense. I'm definitely oversimplifying things in how the adjustment of these weights and these biases work, but it's not crazy important, and we're not going to be doing any of the adjustment ourselves. We are just going to be kind of tweaking a few things with the network. So as long as you understand that when you feed information, what happens is it checks whether the network got it correct or got it incorrect, and then it adjusts the network accordingly. And that is how the learning process works for a neural network. All right, so now it's time to discuss a little bit about activation functions. So right now, what I've actually just described to you is a very advanced technique of linear regression. So essentially, I was saying we are adjusting weights, we're adjusting biases, and essentially we are creating a function that, given the inputs of like X, Y, Z, W, or like left, front, right, we are giving some kind of output. But all we've been doing to do that essentially is just adjusting a linear function, because our degree is only 1, right? We have weights of degree 1 multiplying by values of degree 1, and we're adding some kind of bias. And that kind of reminds you of the form mx plus b. We're literally just adding a bunch of mx plus b's together, which gives us like a fairly complex linear function. But this is really not a great way to do things, because it limits the degree of complexity that our network can actually have to be linear. And that's not what we want. So now we have to talk about activation functions. So if you understand everything that I've talked about so far, you're doing amazing. This is great. You understand that essentially the way that the network works is you feed information in and it adjusts these weights and biases. There's a specific way it does that, which we'll talk about later. And then you get some kind of output, and based on that output, you're trying to adjust the weights and biases and all that, right? So now what we need to do is talk about activation functions. And what an activation function does is it's essentially a non-linear function that will allow you to add a degree of complexity to your network so that you can have more of a function that's like this, as opposed to a function that is a straight line. So an example of an activation function is something like a sigmoid function. Now a sigmoid function, what it does is it'll map any value you give it in between the value of -1 and 1. So, for example, when we create this network, our output might be like the number 7. Now, this number 7, well, it is closer to 1 than it is to 0, so we might deem that a correct answer, or we might say that this is actually way off because it's way above 1, right? But what we want to do essentially is in our output layer, we only want our values to be within a certain range. We want them to be, in this case, between 0 and 1, or maybe we want them to be between -1 and 1, saying like how close we are to 0, making that decision, how close we are to 1, something like that, right? So what this sigmoid activation function does, it's a nonlinear function, and it takes any value, and essentially the closer that value is to infinity, the closer the output is to 1. And the closer that value is to -infinity, the closer that output is to -1. So what it does is it adds a degree of complexity to our network. Now, if you're not a high level like math student, or you only know like very basic high school math, this might not really make sense to you. But essentially the degree of something, right, is honestly how complex it can get. If you have like a degree 9 function, then what you could do is you can have some crazy kind of curve and stuff going on, especially in multiple dimensions, that will just make things like much more complex. So for example, if you have like a degree 9 function, you can have curves that are going like this, like all around here, that are mapping your different values. And if you only have a linear function, well, you can only have a straight line, which limits your degree of complexity by a significant amount. Now, what these activation functions also do is they shrink down your data so that it is not as large. So for example, right, like say we're working with data that is like hundreds of thousands of like characters long or digits, we'd want to shrink that into like normalize that data so that it's easier to actually work with. So let me give you a more practical example of how to use the activation function. I talked about what sigmoid does. What we would do is we would take this weighted sum. So we did the sum of wi, vi plus bi, right? And we would apply an activation function to this. So we would say maybe our activation function is f of x, and we would say f of this, and this gives us some value, which is now going to be our output neuron. And the reason we do that, again, is so that when we are adjusting our weights and biases, and we add that activation function in now, we can have a way more complex function, as opposed to just having the kind of linear regression straight line, which is what I've talked about in my other machine learning courses. So if this is kind of going a little bit over your head, it may be my lack of explaining it. I'd love to hear in the comments below how you think of this explanation, but essentially that's what the activation function does. Now, another activation function that is very popular and is actually used way more than sigmoid nowadays is known as rectify linear unit. And what this does is let me draw it in red actually so we can see it better, is it takes all of the values that are negative and automatically puts them to 0, and takes all of the values that are positive and just makes them more positive, essentially, or like to some level positive, right? And what this again is going to do is it's a nonlinear function, so it's going to enhance the complexity of our model and just make our data points in between the range 0 and positive infinity, which is better than having between negative infinity and positive infinity for when we're calculating error. All right, last thing to talk about for neural networks in this video, I'm trying to kind of get everything like briefly into one long video, is a loss function. So this is again going to help us understand how these weights and these biases are actually adjusted. So we know that they're adjusted, and we know that what we do is we look at the output and we compare it to what the output should be from our test data. And then we say, okay, let's adjust the weights and the biases accordingly. But how do we adjust that? And how do we know how far off we are, how much to tune by, if an adjustment even needs to be made? Well, we use what's known as a loss function. So a loss function essentially is a way of calculating error. Now there's a ton of different loss functions. Some of them are like mean squared error. That's the name of one of them. I think one is like, I can't even remember the name of this one, but there's a bunch of very popular ones. If you know some, leave them in the comments. I'd love to hear all the different ones. But anyways, what the loss function will do is tell you how wrong your answer is. Because, let's think about this, right? If you get an answer of, let's say, maybe our output is like 0.79, and the actual answer was 1. Well, that's pretty close. Like, that's pretty close to 1. But right now, all we're going to get is the fact that we were 0.21 off. Okay, so 0.21 off, so adjust the weights a certain degree based on 0.21. But the thing is, what if we get like 0.85? Well, this is significantly better than 0.79, but this is only going to say that we were better by, what is this, 0.15. So we're still going to do a significant amount of adjusting to the weights and the biases. So what we need to do is we need to apply a loss function to this that will give us a better kind of degree of like how wrong or how right we were. Now, these loss functions are, again, not linear loss functions, which means that we're going to add a higher degree of complexity to our model, which will allow us to create way more complex models and neural networks that can solve better problems. I don't really want to talk about loss functions too much because I'm definitely no expert on how they work, but essentially what you do is you're comparing the output to the what the output should be, so like whatever the model generated based on what it should be, and then you're going to get some value, and based on that value you are going to adjust the biases and the weights accordingly. The reason we use get loss function again is because we want a higher degree of complexity. They're non-linear, and you know, if you get 0, if you're 99%, like say you're 0.1 away from the correct answer, we probably want to adjust the weights very, very little. But if you're like way off the answer, you're 2 whole points, maybe our answer is -1 and we want it to be 1, well, we want to adjust the model like crazy, right? Because that model was horribly wrong. It wasn't even close. So we would adjust it way more than just like 2 points of adjustment, right? We'd adjust it based on whatever that loss function gave to us. So anyways, this has kind of been my explanation of a neural network. I want to state right here for everyone that I am no pro on neural networks. This is my understanding. There might be some stuff that's a little bit flawed or some areas that I skipped over. And quickly, actually, because I know some people are probably going to say this, when you're creating neural networks as well, you have another thing that is called hidden layers. So right now we've only been using 2 layers, but in most neural networks, what you have is a ton of different input neurons that connect to what's known as a hidden layer or multiple hidden layers of neurons. So let's say we have like an architecture maybe that looks something like this. So all these connections, and then these ones connect to this. And what this allows you to do is have way more complex models that can solve way more difficult problems, because you can generate different combinations of inputs and hidden, what is known as hidden layer neurons, to solve your problem and have more weights and more biases to adjust, which means you can on average be more accurate to produce certain models. So you can have crazy neural networks that look something like this, but with way more neurons and way more layers and all this kind of stuff. I just wanted to show a very basic network today because I didn't want to go in and talk about like a ton of stuff, especially because I know a lot of people that watch my videos are not pro math guys, are just trying to get a basic understanding and be able to implement some of this stuff. So anyways, again, that has been my understanding. If you guys have any questions, please leave them below or join my Discord server and feel free to ask. I'm always helping people out. With that being said, if you guys enjoyed the video, please make sure you leave a like and subscribe, and I will see you again in the next one.